Alright, so hello everyone. Today before we start off the video, I guess I should say what my plans are for this series. I've kind of been looking through what I have left in my books and how much time I have left to do this. And so we were going to start Bourbaki today. I looked at Bourbaki, honestly, there's an obscene amount of Bourbaki left, and I'm gonna be honest, I have been doing homework, but I'm kind of behind on it. I need to commit more time to that, and I don't think we'll even have enough time to get through Bourbaki anyways, but I don't want to leave this course unfinished. So what we're gonna do, we're gonna work through our discussion of Lie groups exclusively through Ser. There's still a healthy amount in there, and then when we get done that, then I think I'll call it the end of this course, at least for now. Hopefully that's alright. I know no one actually watches these, but whatever. So with that in mind, we're going to start our new section, which is ominously titled Lie Theory. And this is our new chapter. Throughout the chapter, K is going to be a field. It's going to be complete with respect to a non-trivial absolute value. Alright, and then next, our first topic is going to be the Lie algebra of an analytic group chunk. So at the start of this series, I keep mentioning recently, I mentioned there's a relation between Lie groups and Lie algebras. So I'm thinking here is where we're going to actually finally expand upon that relation and why they're both Lie things. Why they're similarly named in that. Being presented together, these ideas of a Lie group and a Lie algebra, which otherwise has made the course seem kind of disjoint so far. So we're going to suppose f of x and y is a formal group law over K. We know, first off, that f of x plus y is x plus y plus a bilinear form on x and y plus some higher order terms. And we know that for x, y, bracket f being the commutator essentially of this bilinear form, and for this being the bracket, we have a Lie algebra on our K to the n. Which we say is the Lie algebra associated to the formal group F. Now we're going to suppose G is an analytic group chunk over K. We're going to let L of our group be equal to our group be equal to, well, L of our group is equal to the small g is the tangent space at the identity of G, as I said. You see, I wasn't lying. And we define a canonical Lie algebra structure on G as, I'm going to choose a chart C being U phi n of G, sorry my chair is making noises, at E. Then the group law on G is induced via phi from a formal group law F formal group law F on K to the N. So then we're going to let phi bar be the isomorphism from G to the K, G to K to the N, be the isomorphism determined by phi. Then we're going to define phi bar of x, y, of the C, we're going to have the C bracket of x and y, for where C is our chart, be phi bar of x, phi bar of y in our F bracket. Now we of course need this C bracket to be independent of our choice of chart, which motivates a lemma. Move the chair because it's off balance. Lemma. G and G prime be analytic group chunks. C and C prime be charts at E. And E prime, and we're going to let F from G to G prime be a local homomorphism. Then the induced tangent, sending elements of G to G prime, small g of course, is a Lie algebra homomorphism with respect to the chart brackets and we prove this by a second lemma where we let f of x and y and f prime of x prime and y prime be two formal group laws, and we're going to let f be a formal homomorphism from F and F prime. And we are going to let F1 be the linear part of F. Then our limit is that we have the F prime bracket of F1 of X and F1 of Y be F1 of the F bracket of X and Y. Now our proof, we have F of X inverse the commutator of F of X and F of Y we have seen is going to be F1X, F1Y, the F prime bracket, plus higher order terms. F of X inverse Y inverse X, Y being F1 of the commutator of X and Y in F plus higher order terms. And so by comparing terms of degree 2, we get our lemmas. And from the above, we get in such a case, G with its canonical Lie algebra structure is said to be the Lie algebra of G. It says that our lemma also gives that the construction of the Lie algebra of a group chunk is functorial. Also, I did not start a timer on my phone, so I'm going to have to... Oh, okay, and then something just crashed. Sorry, you'll have to give me a second because everything is breaking all of a sudden, as it does. So while I'm getting this set up, I know our next section is going to be elementary examples and properties. Yeah, so it's been like 14 minutes. Alright, sorry about that. So, our first example is going to be the Lie algebra of a general linear group. I think you can probably guess what it's going to be, but let's work through it. Now, suppose R is an associative algebra with unit, finite dimensional over K. then GM of R, not GL, so it's a bit more general, we know is an analytic group, and it is an open subset of R. So T1 of GM of R is just R. As you'd expect from what we had our general linear Lie algebra be. Multiplication in GM of R has the form where 1 plus x, 1 plus y is 1 plus x plus y plus xy, with, of course, our formal group law, just by making these 1 pluses implicit, so f of x and y is x plus y plus xy. Hence, the Lie algebra structure on T1GMR, which is R, is, keep in mind, is just the commutator of the bilinear form. In our case, the bilinear form is just multiplying the two inputs together. So our bracket is going to be xy minus yx, the standard matrix bracket, a standard bracket, in fact, which will, of course, as you saw, give the usual Lie algebra structure when R is the endomorphism ring of a finite dimensional vector space. Alright, secondly, we're going to start getting into some more abstract details. The Lie algebra of a product. Suppose G1 and G2 are analytic groups. Then the linear isomorphism of the tangent space of the identity of G1 and G2 with the tangent space of G1 and the tangent space at E of G2. It looks like a 6. Is a Lie algebra isomorphism. So essentially this is saying that the product of the Lie algebra of the product of Lie groups is the Cartesian product of the corresponding Lie algebras. And so we're going to let CI be a chart at EI on GI, and we're going to let C be C1 times C2. Then the product of the Ci brackets is the C brackets. Alright. Thirdly, we look at the Lie algebra of a group submanifold. Suppose G and H are analytic groups, and F from H to G is an analytic group homomorphism and is an immersion. Then L of F being a map from L of H to L of G is of course going to be injective. So L of H is identified with a Lie subalgebra of L of G. Let me just apply to H being a group submanifold of G and F the appropriate inclusion. Now we can say a bit more in a particular case. So let's suppose we're in character 0, and we're going to let H1, H2 be group submanifolds of G. Then the intersection of H1 and H2 is a group submanifold of G and oh, my phone is once again freaking out. Sorry, you'll have to give me 1 second here. Then L, the algebra of H1 and H2 is the intersection of the algebras. So our proof, we know that G over H1 is a manifold. Let X be the coset H1 in G over H1. Then H2 acts on G over H1 and the stabilizer of X1 being X, H1 being X, is the intersection of H1 and H2. Since we're in characteristic 0, H1 intersecting H2 is a group submanifold of G. And we can identify the Lie algebra of their intersection with its image in LG being the kernel of the map from the tangent at the identity of H2 to the tangent at the identity of G over the tangent at the identity of H1. Which is LH1 intersecting LH2. This comes with a corollary, of course. Suppose that the algebra of H1 is inside the algebra of H2. Then in a neighborhood of E, H1 is inside H2. And the proof. So we know that the tangent at the identity of H1 intersect H2 is the intersection of the algebras of H1 and H2, which in this case is going to, by assumption, be the algebra of H1, which is the tangent space at the identity of H1. And so we know that H1 intersected H2 is by definition obviously going to be in H1. Hence H1 intersect H2 and H1 agree in a neighborhood of the identity. We have an immediate corollary, where if we just take this in inclusion both ways, so if two algebras match up, then in a neighborhood of E, these submanifolds have to match up themselves. There's another corollary where we're going to let G1 and G2 be analytic groups. And let phi and psi from G1, phi and psi from G1 to G2 be analytic group homomorphisms. Then psi and phi agree in a neighborhood of E1 if and only if their associated algebra maps match up. And we should actually go ahead and prove this one. The graphs G phi and G psi of phi psi in G1 and G2 are group submanifolds. And from a previous identification, we have L of G phi being the set of pairs in L of G1 times G2, where Y is the image under L of phi of X. And likewise, we have L of G of C defined in much the same way. G1 times G2, where Y is L of C of X. So they're the charts, I believe, of these functions, is how you'd call that, potentially. So by our previous corollary, the following are equivalent. First off, V and C agree in a neighborhood of E1. G phi and G psi agree in a neighborhood of E1 comma E2, and we can get from that their charts match up. Not their charts, their Lie associated algebra maps. You know what I'm talking about. And fourth and final example is going to be the Lie algebra of a kernel. Suppose G and H are analytic groups, and phi from G to H is an analytic group homomorphism and a subimmersion. We're going to let K be the kernel of this map. This should be a capital K to be less confusing, actually. Then K is a group submanifold of G, and L of K is the kernel of the tangent of density of phi, which is going to be X in the Lie group, the Lie algebra of G, where L of phi, L phi of X is 0. Alright, and up next we're looking at linear representations. And that's going to be in the Campbell-Hausdorff formula, which we covered earlier, so I might want to review that for next video if we get to that. And yeah. I mean, wait, how long is the next chapter? I thought. Man. My timer got all screwed up. You know what? Well, how long will be doing a new? How long will be doing a new section take? You know what? I mean, we need to get through this. Let's do. I'm sorry for like having a full solid minute of dead air while I just flounder around through my book. But let's get started on the next chapter. I kind of got lost there too, so what I said was coming up, I don't think is coming up actually, which is pretty cool. Fun fact, keep you on your toes, you know? So, our next topic in this chapter is going to be linear representations, not whatever it was that I said. So we let G be a Lie group and V be a vector space. A linear representation of G and V is an analytic group homomorphism sigma from G to the general linear Lie group of V. Then G acts on V by sigma. So say an element of G acting on an element of V is sigma being sending G to a linear automorphism of V, which then acts on V. From sigma, we obtain an induced representation of L of G by the induced homomorphism sigma bar from L of G to the endomorphisms of V of Lie algebras. And our first section here is going to be basic examples. I mean, first off, we have the identity, obviously, of GLV acting on itself. Two, you can define the map, which can write as an asterisk, from the general linear Lie group of V to the general linear Lie group of its dual. As the element U being sent to U transpose inverse. Or maybe, I think inverse transpose would be, I don't know which way is better. Then this star is a Lie group isomorphism. We're going to let 1 be the identity of V and 1 star be the identity of V star. Then in a neighborhood of 1, we have star of 1 plus x being 1 star plus x transpose, all of this inverted. So you know what, just to make it less confusing, I will write this as transpose first. I'm pretty sure they commute, but I don't know. Why not, right? Which is the sum over mu from 0 to infinity of -1 to the mu times x transpose to the mu, which is 1 star minus x transpose plus higher order terms as you do. With the algebra equivalent of star on x being negative x transpose. Okay. Third, we're going to do this on a new page. We're going to let the collection of vi from 1 to n be vector spaces. And we're going to set v to be the tensor of all of these. We're then going to define theta being the map from the endomorphisms of v1 through the endomorphism algebra of vn to the endomorphism algebra of v by theta of u1 through un being the tensor from 1 to n of ui. Then theta induces a Lie group homomorphism of the products of all our general linear Lie groups to GL of v, and in a neighborhood of 1 in G being, of course, the product of our GLVIs, we have theta of 1 plus x1 through 1 plus xn being 1 plus the sum from 1 to n of the tensor products of a bunch of 1s with the ith component being xi and then higher order terms with then L of theta of x1 through xn being this sum of ith 1 through n of tensors of a bunch of 1s with xi in the nth component. Example 4. Let v1 through vn and w be vector spaces and set v to be the linear maps from v1 through vn onto w. And we're going to set g to be the product of all of the general linear Lie groups of all of our vi with the general linear Lie group of our w. Then V is canonically isomorphic to the tensor product of all of our VI stars, then tensored with W, regular. We can then obtain a map from our previous examples, theta from G to GL of V by theta of U1 through UN through W on V, being W composed with V composed with the tensor product from 1 to N of UI inverse. With then L of theta of x1 through xn and z of y, being z composed with y minus the sum from 1 to n of y composed with the tensor of 1 in all of our indices except for the ith component, being xi. And we have one final map we're going to consider, and then I think we can call it for an episode. Let me double check that. Yeah, okay. Now we're at a reasonable time. Sorry about that false setting. I do that too often. I should check the time better. So we're going to let G be GLV and consider the determinant map from G to GM of K being the, as I said, which is going to be the determinant map. And review K star as GM of K in a neighborhood of 1 in G, the determinant of 1 plus x is 1 plus the trace of x all the way through the determinant of x, which is 1 plus the trace of x plus higher order terms, with TR the trace map. With then L the algebra version of the determinant on x being the trace of x. And since we know that the general linear Lie group, the special linear Lie group we define as having a determinant of exactly 1, that corresponds to having a trace of exactly 0, as you can see by this, hopefully. And yeah, as I said, now we can call an episode. Thanks for watching. Sorry about the mess there.